Dear student friends, in the last lecture we have studied open set definition and some examples we have studied, and we are studying the properties or theorems on open sets. Now here is our second theorem. The first theorem we have proved as the entire set M and the empty set phi both are open. Now the second theorem says that let this script F be any non-empty family of open subsets of a matrix space M, then union of G, where G belongs to script F, means G belongs to the non-empty family of open subsets, is also an open subset of M. So what is the meaning of this in other words is any union, finite or infinite union of open set is an open set. So here F is a family of open sets or open subsets of matrix space, and we are considering the collection of this here or union of that, then that is also open, we have to prove. Now we shall consider the proof. Let us denote this set as H, which is union of G, and G belongs to the family script F. So what this F will be? The collection of these sets G1, G2, G3, etc. Finite or maybe infinite, countable or maybe uncountable, where these are open sets. And now what is the meaning of union of G and G belongs to F will be the union of all the members, all members of this family or this class. So that this will mean G1 union, G2 union, G3 union, etc. So that is the meaning. And if each set is open, then their union, their countable union or uncountable union, whatever the union is, finite or infinite, is again open. That we have proved. And we have denoted this union by H. So H means actually G1 union, G2, etc. And to prove this as open set, we have to use the definition of open set. The definitions are important, and every time we have to use the definition to prove the results. Now one thing here is this H is non-empty. So if every G is empty, then H will be empty, and then also it becomes open set, because we have proved in first theorem empty set is an open set. If each or if every G is empty, then H is empty and is open. This follows by the first theorem. Now suppose at least one G in this collection is not empty, then this H will not be empty. Suppose at least one G belongs to this family. We have to write, we are using different symbols, and here this is script F. So we are denoting this family of open subsets. At least one G belongs to F is non-empty. Now to prove H is open set, to prove H is open set or open subset of M, we have to consider X in H. Now let X belongs to H. To show that H is open, we have to find an open ball, or we have to show that there is an open ball around X of radius R, such that this is contained in H. there is an open ball around X which is contained in H. Now X belongs to H. So this implies X is in H means H is the union of G. Union of G, that means union, G1 union G2 etc. Whatever the members will be there in this family. Yeah. Union is taken over that family. Yeah. So G, X belongs to union of G. And if an element is in the union, then it must be at least one member. So when we say X is in the union of A and B, then X must be at least in A or B. So therefore this X must be one member G of the family. So this implies X belongs to some G. X is in some G belongs to such that G belongs to F. And that G is the F is collection of open sets, so therefore G is open. So this implies, but G is open. Open subset or open set. Therefore by definition of open set, there is an open ball B of radius R around X which is contained in G. See, G is open, G follows the definition of open set, and therefore X is in G, and therefore the open ball around X must also be in G, and thus the open ball is in G, and this G is subset of H, because see, H is collection of union of G, and therefore G is subset of H, but also G is subset of H. Obviously here we can say A is subset of A union B. So H is a union of G, and therefore G is subset of H, and thus what we have is this open ball of radius R about X is subset of G, and G is subset of H, and thus by transitive relation A is subset of B, B is subset of C means A becomes subset of C, and this open ball of radius R around X becomes subset of H, and this is what we wanted to. We have to show that there is an open ball of radius R around X which is contained in H. Hence H is open subset. Hence this H, which is union of G belongs to F, is open subset of M, or open set of M. And this proves that union of any number of union of open set is again open set. Now the next result we shall consider as the consequence of this result as theorem 3. Every subset of RD is open. Now this is simple, because we have seen a singleton subset of RD is always open. Let A belongs to RB, then we have already considered singleton set A, which can be expressed as an open ball around A of radius 1, and that is contained in RB, and therefore this is open. Therefore, every singleton set or one point set in RD is open. And now a subset of RD is union of singleton sets. A subset is a union of one point sets. And see what we have written, every one point set is open, and it is union of one point set means union of open sets, and union of open set is open. Therefore, every subset of RD is open. This is by theorem 2. We have used theorem 2 here. Union of open set is open, and thus this proves every subset of RD is open. Now we shall consider the next theorem as about intersection. We have considered union of two sets, union of any number of subsets of open subsets is again open. Now we shall consider the result about the intersection as our theorem 4. Let G1 and G2 be open subsets of a matrix space M. Here a row is to be assumed. Then G1 intersection G2 is also open, or that is open subset of M. Now this we have to prove. The proof we shall consider now. So we shall assume G1 intersection G2 is not empty, because if it is empty, then that is obviously open, because the empty set is open. We assume that G1 intersection G2 is not equal to empty. Now to prove G1 intersection G2 is open, we consider let X belongs to G1 intersection G2. Let X belongs to G1 intersection G2. Then what we have to prove is this is open. So given that G1 and G2 are both open, if there are two open sets, then their intersection of two open sets is also open. That we have to prove. And for that purpose, we have considered X belongs to G1 intersection G2. And now this we shall have to prove that. To prove this is open, we have to prove that there is an open ball around X of radius R, which is contained in G1 intersection G2. Then this will prove that this G1 intersection G2 is open. Now we shall start with X belongs to G1 intersection G2. Let us consider this X belongs to G1 intersection G2. By definition of intersection of two sets, this implies x belongs to both. X belongs to G1 and x belongs to G2. Now because G1 and G2 are open, there exists an open ball around x which is entirely in G1. Similarly, there exists an open ball around x which is entirely in G2. So this implies there is an open ball around x of radius, say r1. So this is the notation to write the open ball which is contained in G1, and for this case G2 is open and there is an open ball of radius r2 around x that is contained in G2. The reason for this is since G1 and G2 are open, we are using only the definition of open set when the set is said to be open. If any point is considered, then the open ball around that point is again in the same set. Now we will take, there are two open balls around the same point x, r1 and r2. So the case is now like this. See, this is point x and the r1, this is open ball of radius r1. R2 may be less or greater than r1, and if you consider this as r2, then this is open ball of radius r2. Now what we shall consider is x is in this open ball, x is also in the outer open ball, and we will consider r is minimum of r1 and r2. Here that will be r1. Minimum of r1 r2 is r1, and if vice versa may happen, if this is smaller is r2, then minimum will be r2. We take r is equal to minimum of r1 r2. Then this open ball is contained in both G1, a open ball of radius r will be in both G1 and G2. So this is the earlier open ball and this is the open ball of radius r. Then the open ball of radius r, which is minimum of r1 and r2, is contained in both G1 and G2. Is contained in G1 and the same open ball is contained in G2. And if the same open ball is in both G1 and G2, we say it is in the intersection. So therefore, the open ball of radius r about x is contained in the intersection of G1 and G2. And this is what we wanted to show. We have to prove that there is an open ball which is contained in G1 intersection G2, and this proves that G1 intersection G2 is open. Hence, so what is the meaning of this theorem? A finite intersection of open set is open. That is the meaning. Here only we have considered, see the difference in the earlier theorem about union. For union, the union may be of any number of open sets, then that is also open, but then that is not the case for intersection. We can't say that infinite intersection of open set is again open. Only the finite. If G1, G2 is the open sets, we may extend this up to finite. That is G1 intersection G2 intersection up to Gn. When n is finite, will be again open, but that is not true for infinite number of intersection. We write that as a remark. The infinite number of intersection. Intersection of infinite open sets, subsets. Infinite number of open subsets may not be open. For example, we will consider this example. For example, let in be this set. In is equal to the interval minus 1 by n, 1 by n. Then this is open. It is an open interval and therefore open. In is open. N belongs to 1, 2, 3, etc. Every open interval in R1 is open. But what is intersection of In as n takes value 1 to infinity? We are taking infinite intersection. Now can you guess this? What will be this? See, intersection of I1 will be minus 1, 1. Intersection I2 is minus half, half. And intersection minus 1/3, 1/3. Now as n increases, see 1 by n we know tends to 0. And therefore this will be intersection with 0 and 0. And that is 0, single point. And thus the intersection means which contains in every those points which contain in every set, and therefore this intersection contains only 0. So this is 0, and this is not open. 0 singleton set in one point set in R1 is not open, that we have seen earlier, and which is not open. Not open in R1. And thus, though every this interval is open, their intersection, infinite intersection, is not open. And that is the difference in the union and intersection of open sets. If it is infinite, then that may not be open. But finite intersection of open set is open. Now one more note we should consider is, before going to the next theorem, we will have this as in R1, every open interval is an open set. Open interval means open ball, and open ball is open set, that we have proved. So in real numbers, every open interval is open set. Or that means, see, open interval 1 to 2, or the open interval 1, 3, 4, 7, etc. or in general, A, B are all open. Open intervals are open balls and they are open sets. Now what we are going to state is the next theorem as 5. So if we have G, every subset of R1 can be written as union of open intervals I, that we shall prove as our next result. This is theorem 5. Every open subset G of R1 can be written as G is equal to union of IM, where I1, I2, etc. are the finite number or countable number. Countable number of mutually disjoint intervals. Mutually disjoint in open intervals means that is, or it can be written as that is, IM intersection IN is empty if M is not equal to N. So this is the result that we have to prove. Every open set in R1, open subset of R1, actually it is open interval and can be written as again union of intervals. So for example, we may consider G as, it is open interval may be considered as say 3 and 10. And this can be having the points from 3 to 10. Now this can be covered by making another intervals, disjoint intervals, whose union will make this up to the interval 3 to 10. So this may be taken as I1, I2, etc. and so on, say whatever it may be. So therefore G is taken as union of open intervals. Every interval can be taken as union of open intervals I. That is to be proved. Now we have to prove this, let G be open subset of R1. And write as a solution or proof for the theorem. Let G be open subset let X belongs to G. By definition of open set, there is a open ball around X which is contained in G. Then there is an open ball which is open interval B. Open interval, here it is open ball. We have seen for R1 open interval are open balls. Open interval B contained in G. Now let Ix be the largest open interval containing X. And this Ix is contained in G. So this we are considering, say X is in G, that we have taken. Suppose this is G and we have taken some X here. So this X will be contained in Ix. Ix is the largest open interval containing X and Ix is contained in G. So that depends on this. That will be Ix. Actually the whole interval G will be the largest, which contain X, and that is the meaning of Ix. Ix is defined as, or this is the general interval B. The X is in G, then there is an open interval B which is contained in X. There is open ball B which contains X and that is contained in G. Now let Ix be the largest open interval containing x, and that Ix is subset of G. Then G is union of all such Ix, and this union is disjoint, and Im is equal to, or instead of Im we will use Ix. If here if you consider x and y are two elements in G, xy belongs to G, then the open interval containing x is denoted by Ix, and the interval which contain y will be denoted by Iy, that is largest. So then Ix is equal to Iy, or this Ix intersection Iy is equal to phi. So this is the case we will have. And for if this is not the case, that means each interval containing x, that is Ix, largest interval. Suppose this is the point y, then that the interval is Iy. So these two intervals are either equal or they are disjoint. So mutually disjoint means no point in common, and if one point is common, then they must be exactly equal. Now we will prove this for, because if suppose if Ix is not equal to Iy and Ix intersection Iy is not equal to phi, then if both are not true, then the union, then Ix union Iy is the largest interval, or is the interval which contains x. See, the case is now like this. If this is x and this is Ix and this is y, and we are considering they are not disjoint, means this is Iy. Now their union, Ix union Iy, will be the set from this to this. And this contains x, this contains x. But this is a contradiction, because what we have denoted here, or we have assumed here, let Ix be the largest open interval containing x. And that this is a contradiction. Then is an interval greater than Ix. Containing x. And is a subset of G. So this is a contradiction. This is a contradiction to the definition of Ix. Definition of Ix means we have defined the Ix here. Ix is largest open interval, and thus these are either equal or mutually disjoint. This case does not happen. That means if this is the interval containing x, then the interval containing y is disjoint, separate, and then the whole set G will be covered by all such disjoint intervals. Further, each disjoint interval contains a rational number. So we may consider that further each disjoint interval or each open interval contains a rational number. And say disjoint interval cannot contain the same rational number. and since the rational numbers are countable, we have the countable number of unions, and we have G is covered by these countable number of open intervals, where IN is open intervals or IN are open intervals which are mutually disjoint. And this is what we wanted to prove. So what we have as an open set, and that open set can be partitioned or can be divided in disjoint number of open intervals to cover this set. So that is the meaning of this theorem. So remaining theorem we will consider next time. Thank you.